Ngalakin Khadijan Nyunga Boja.
Video 30, indexes. So indexes is a topic related to the practical performance of a database, and it's most relevant for very large databases. We've only really investigated pretty small databases so far. It's also an area where the different implementations of SQL, so MySQL, SQLite, PostgreSQL, and so on, they will vary more in their implementation of indexes than in their implementation of sort of fundamental SQL constructs. Okay, so basically a lot of the time a database is going to be trying to look up specific values in a possibly very large table. Here's sort of a silly example which shows some names. Now, in this case, the names are actually sorted alphabetically. So Mr. Aardvark is at the beginning and Mrs. Zippo is at the end. And then each of these names, they have an ID number or something associated with them. And so the ID numbers are stored in the second column. The data in the second column is not sorted. The IDs can occur in sort of any random order at all. Okay, so suppose that frequently we want to find the ID number if we are given a name. So we have to look up the name in the name column and then read off the data in the ID column. This is just a little example. Obviously, in reality, there'd be many more columns in this table, but still the fundamental principle is we want to try to find which row contains a specific value as quickly as possible. Okay, one sort of secret that we should let you in on is that SQL actually keeps track of a number called rowid for each row of a table. You can arrange for this to be turned off so it doesn't keep the rowid, but in general, the table will have a rowid column. It will sort of be semi-visible in that it will appear if you say select rowid, but if you select star, then it won't appear. So this is in the background. Okay, in this table, I've put a billion rows. I mean, this hypothetical table, I've put a billion rows, and that's 2 to the 30 rows. Okay, so the task then is, if I give you a name, let's find which rowid contains the row with that name in it. Okay. So we're trying to look up the name for Mr. Snodgrass. If we can find out which row number has Snodgrass as the name field, then we can immediately read the data straight off the disk. Because of course, SQLite will always keep track of, where on the disk is the information for rowid 2, where on the disk is the information for rowid a billion. Like it'll keep an array of disk locations or pointers, and so given the row number, we can very quickly find the rest of the data. Okay, so how hard is it then to find that particular value in the table? To decide how hard, or to discuss how hard it is, we're going to talk about how many times you need to actually look at a value in a particular column. So one operation of looking at the value is called a probe. So what we want to do is find Snodgrass using as few probes as possible, because each probe is some actual work that's being done, like some memory location has to be read off disk and its value examined. If we have no information about how the data is stored in the table, then there is simply no choice but to do a linear search. So the database management program will look at row 1. Is the name equal to Snodgrass? No. Row 2. is the name equal to Snodgrass? No. Row 3, is the name equal to Snodgrass? And so on. That means that a query like select everything where the name is Snodgrass will require the database management system to examine every one of the rows. All billion of the rows will have to be examined just to find the one row that is Snodgrass, or perhaps there are several rows that are Snodgrasses, or maybe Snodgrass isn't there at all, in which case it will just look through the whole database and not find anything. Okay, if we know, or we're told, that the name column is sorted in alphabetical order, or rather if we tell the database that the name column is sorted in alphabetical order, then you can do a dramatically better way of finding the name Snodgrass, if it's there, which is to do a binary search. Now, I don't want to get into too much detail about what a binary search is, so I'm just going to do a little example and informally hope that you can sort of understand roughly how it works. Okay, so I've got here a little array of 32 boxes. What I want you to think of is this is actually the billion rows. So except I just can't draw a billion rows. Okay, if Snodgrass is anywhere, Snodgrass must be after the leftmost, row 1, and to the left of row 1 billion, or in this case, row 32. Okay, so somewhere in there is Snodgrass. What we can do is we can do a single probe in the middle of the table. Okay, so we go to the middle of the table and do a probe and look at that value. Okay, suppose that value is Michael's. Well, then now we know that wherever Snodgrass is, if Snodgrass is in the table at all, it has to be between in this range here. Because the data is sorted, we know that everything down here occurs before Michael's, and Snodgrass definitely appears after Michael's. Okay, so by doing one probe, we've eliminated half of the rows as being possibilities. Okay, now we do another probe in the middle of this new range, I guess there, and if we discover that one is, say, Thomas, well, then we know that Snodgrass is between M and T, S is between M and T, so now we've eliminated, now we only have to look at this range, which is only a quarter of the size of the original thing. So each probe then will throw out half of the rows as being possibilities for to contain Snodgrass. So that means that by the time we've done 30 probes, then the length of the range is only 1, and so we've either found Snodgrass or Snodgrass is not there. So that means that instead of taking a billion probes, we're only going to take 30 to find this. Okay, that is the power of sorting. Normally at this stage, I would give the example of looking up a person's number in a phone book as an example of a sort of human-operated binary search, but probably a significant proportion of you have never actually seen a phone book. So certainly phone books have been, phone books basically don't exist anymore. Okay. So in general, if your database has n rows, okay, and we have the we've got, sorry, name and ID. If I give you the ID and ask you to find the name, well then the values in this column are not sorted, so you have no choice except to look at each of the values in turn, and that will take, on average, n/2 probes. I say on average because if the thing you're looking for happens to be at the very top of the database, then you'll find it immediately. If it's at the very bottom, you won't find it till you've looked at every row. But on average, n over 2. On the other hand, because the names are sorted, that means we can very, very quickly locate the row that contains the name, and that will only take about log to the base 2 of n probes. This is an absolutely huge difference. Something that's n over 2 versus something that's log n, there's the log n, the log to the base 2 of n will scale up to billions and billions and billions. The n over 2 will sort of will really start to fade after you get to a few thousand billion. Okay. Right, I've given the example of a binary search as an example of a mechanism for finding a value very quickly. Now, databases, what a database can provide is it allows you to create an index on a particular column in the database. Now, an index then is sort of an additional data structure that contains the data in, roughly speaking, sorted order, and therefore has something that's like a binary search that provides very rapid access to the rows that contain a specific value. Okay, I'm being a bit coy here about what this actually is, what the data structure actually is. It's actually something called a balanced tree or a B tree. So it's not quite like sorting the data, but it has the same effect. Okay, the effect is that if you want to look up a value and you've stored it in a B tree, then you can find that value in about log to the base 2 of the number of items stored. So B tree is a data structure that provides benefits similar to a binary search, but it isn't actually a binary search. The reason I don't want to go into what a B tree is because that's itself is sort of a topic that would require quite a lot of, several slides. And as far as this unit's concerned, we're not so interested in how the index is implemented. We're really interested in what the index gives the user. Okay, so let's start with an example. I'm going to create a table, which I'm calling index test. It's going to have a name, which is some text. That's going to be eventually I'm just going to use some sort of random character data in there. And id, which is an integer. And we're going to investigate how fast it is to find a particular name and how fast it is to find a particular id. And then we're going to add some indexes, and then we're going to see how that time changes. Okay, so I created on my computer some random data for this particular task. The name is actually sorted, and we're not going to use the fact that it's sorted, but it's just for convenience. And then there's a random number as the ID. So how many rows have I put in this table? I put 312 million in there. 31 million in there. It took even 2.326 seconds even to just count the number of rows in the table. Okay, you'll notice that I'm doing this in the PowerShell or the terminal version for SQLite, because the SQLite Studio doesn't report the times properly. So what I've done is I've just opened up SQLite. I've put the timer on. So it's a dot command, dot timer on. After that, it will report to me for each command how long it took. Real is the actual real elapsed time. That's like 2.3 seconds. User is the amount of CPU time that the user consumed. Sys is the amount of system time that the process or the command consumed. So basically, user plus sys should be about the same as the real time. If there are many, many other users on the machine, then the real time might go bigger, even though the actual time used by the command is still the same. Okay, So user you can think of as being mostly the CPU time, and sys you can think of as being mostly sort of system operations, in particular disk operations, extracting the data from a disk. Now this will be much slower if you're using a spinning disk like an old-fashioned hard drive. If you've got a solid-state drive like most people will, then it will be fairly fast. Okay, this next one is something that's outside. So I'm in the terminal and I'm doing a command. This is a Mac command. There must be some Windows equivalent. It's just going to tell me how much disk the database is consuming. And how much is it consuming? 6.2 gigabytes. So I've got a 6.2 gigabyte file containing my 31 million rows. I've chosen that size because that gives us enough of a size so that normal things take a bit of time and we can see the speed up. The things that we've been doing so far with like 1 million rows or something, the computers are so fast these days that that you can barely see any difference. Okay, so let's see how long things take. Suppose I give it a name and ask for the ID. Now I happen to have asked for the for one right at the beginning, but it doesn't matter because I know that because I've got select star, it's going to have to examine every row. Finds one row as the output, no problem. What we're interested in is how long it took. About 15 seconds. So it takes about 15 seconds to look at each of the 31 million rows and compare them with 00001A and then either keep or not keep. Okay, for the reverse, because this one produces, so I'm going to give an ID and then see which, which rows had that particular ID. But instead of printing out the rows, I'm just going to count them. The reason is that ID has got lots of repeated values, whereas name has got no repeated values. They're all unique. Anyway, counting the number where the ID was 150,000 took about 12 seconds. So roughly speaking, 12 to 15 seconds to do a linear search to find those values. If we know that we're going to be looking up something very quickly, then we can add an index to the column. So that says, compute for me this special data structure, which is called a balanced tree or a B tree, and store that with the database in the same file. So this is an extra data structure, an auxiliary data structure, but which sort of is stored along with the data in the same file, and SQLite sorts all the details out. How do we do it? Well, we say create index, then we give the index a name, then we say which table we wanted the index to be placed on, and which column from that table. So what that does is it essentially takes, well, do I have an example? I will. Okay, so here is my example. I'm creating an index. I'm going to call it IDX. The name doesn't matter. It's just if we want to delete it later. And it's going to be on the name field of the table index test. Okay, so, and then it goes away and it builds this B tree. So to build the B tree, it has to put all of the values of name into this new data structure. This new data structure is carefully chosen so that it is very rapid to search for particular values. It's not quite the same as sort of forming a linear order of the names, but it's approximately equivalent to that. So doing this calculation takes a long time, over 2 minutes. So I sat there for 2 minutes waiting for it to do all the calculations. It also takes a lot of space because essentially we've now got 2 copies of all of the data in the name field. One copy is in the original tables, and now we've got a new copy of that in the B tree, the balanced tree. So we've essentially doubled our storage requirements. Now, that may or may not matter. Okay, now what happens when we want to use this Well, we don't have to do anything special to say use the index. As long as we've created the index, then SQLite will know that it's there. So if I now do a select star where name equals 1F3, then the time, well, it's found the right one, and the time it's taken is now 1,000th of a second, or essentially so small that can barely be counted. So producing this index has dropped our searches from 13 seconds to 1,000th of a second. So that's like 10 to the 5 times faster. Wow. So that is an amazing speed up. And the reason is that that the index has stored this data in a particular way that makes it very easy to access based on the values of the data. The table that we haven't chosen the index for, well, we're still no good, still slow. Okay, so it's quite clear now. If you very, very often have to look up the id given the name, then put an index on the name. If you have to do it the other way around, then put an index on the id. So under certain situations, you will want to carefully analyze what indexes you should put on the tables. Okay, if I now create another index, or a second index, it's on the id column. Now that takes even longer to do the indexing, to create the B tree, but once the B tree is created, it's just there. You don't have to recreate it again. And if we now do a query that involves id, even sort of a query that's not all that easy, like where the id is between 100 and 200, well, just took 1,000th of a second again. So an index takes a query that takes 13 seconds and improves its performance by 100,000 times. Okay, so your boss, if you work in a database situation and you can make your boss's queries 100,000 times faster, then you will be in good shape. Okay, but not every query. What happens if I select count star where id %1000 is 0? Well, id %1000 is just the remainder after you divide by 1,000. So it's just the last 3 digits of id. Now, of course, the ID number, we have an index on ID. And so if you're given an ID number or range, then it will look it up blindingly fast. But if we give it an expression involving ID, then it doesn't know that the index can be used. So we can't use it. Well, if you discover then that actually almost always when you're doing the queries, you actually use just the last 3 digits of ID, then of course you would say to yourself, well, really, I don't care about an index on ID itself. What I care about is an index that locates values of ID %1000 very quickly. And of course, SQLite allows you to do that because instead of the name of a column for your index, you can use an expression involving the column. And that's called an expression-based index. And once we've added the expression-based index, then as soon as the system sees ID %1000, then it knows, aha, that's the values that I need to be looking up very rapidly. And again, we get this same multi-thousand factor of improved performance. But okay, I think actually I'm going to ignore that slide because it's got the wrong picture in it and it's getting too complicated. So basically I'm just telling you that an expression-based index does exist. We're not going to be using it. Okay, now the trouble with an index, of course, is that you've got this huge data structure that stores all of the data, but in now a convenient form to access rapidly. What happens if one of the rows changes? Well, if a row of an indexed column changes, well, then the index has to change as well. So every time an insert happens or a delete happens, then SQLite will have to insert the new row into the table and then insert it into the index. Now, inserting it into the index is maybe problematic because the whole point of an index is that it stores the data in a very particular sort of structured order, and the new data may cause quite a few things to change in the index. Okay. It doesn't matter in the sense that you have to do anything because it's all done automatically, but it will take some time. So, in summary then, under these situations, you should consider adding an index to your columns. If the data is large or very large, say hundreds of millions or billions of rows, if it's very frequently queried, maybe often using a particular column, and if it's not changing too much, then you would choose to add an index to the columns that are being used most often. If you want to delete an index, then you just use drop index, which is sort of similar to drop table and all the rest of it. Takes a little bit of time to drop the index, but not nearly as much as creating it. So now I've dropped both my index and my beta index and so on. But if you were to look at your file system, you would discover that even with the indexes deleted, the size of the file is still very large, 19 gigabytes. Now, the point is that when you delete an index, SQLite doesn't sort of repack the file so it's nice and sort of compact. It just keeps a little, it just marks that space as being currently unused, and it will then use that space if you add more information to the database. On the other hand, if you actually want the file size to shrink properly, so you want it to recover the unused space, to recalculate the row id, and overwrite the database file, then you should run the... so if you want to tidy up the file, recover the used space, have it rearranged in as compact form as it can, then you just run the vacuum command, and that does all that work. As you can see, vacuuming up the empty space takes quite a bit of time, but you get a nice satisfactory reduction in the file size. So the 10 gig file there is the original 5 gigabytes or 6 gigabytes of data, plus the one index that I didn't remove with those two drop index commands. Okay, SQLite gives you a number of automatic indexes, which means the data is initially set up in a sort of indexed fashion, and in particular, if it's a primary key column. So if you have a column that's defined to be a primary key, then SQLite knows that this is going to likely be involved in join statements because you'll be joining tables by their keys. It's probably going to be involved in foreign key constraints. It's probably going to be used in subqueries and so on. So in other words, it's got, the chances are that you're going to be doing a large number of looking up that value for that particular, looking up a value for that particular column, in which case you should declare it to be a primary key and the index will automatically be created. Final little bit is composite indexes. If your queries often ask for information based on a combination of values in two different columns, then you can choose to index that combination of columns. So instead of having just one column in the on table name thing, then you can name two columns, column name 1, column name 2. Then queries that do involve both of those columns will benefit. given a particular value for column 1 and a particular value for column 2, it will almost instantly be able to find the rows that have those particular values. Okay, final sort of thoughts. Suppose I create an index called double index on, and I haven't given a table name here. I think I couldn't decide what name to give it. So R of AB. Then the data in the index is going to be organized firstly according to the value of A, and then within each value of A, the value of B. Now this isn't exactly the sort of format, but this is good enough to sort of understand how things work. So we'll have, like, A being 10 and then all the different values of B. So somewhere in this database then there's columns with AB equals 10.1, 10.2, 10.5, 10.10, and so on. So it'll basically arrange them in this sort of fashion. So the A values will be sorted, and then within each A value, the B values will be sorted. Again, not exactly sorted, but rapidly accessible as though they were sorted. Let's look at these queries. Select star from the table where A is 18 and B is 7. Okay, A is 18, B is 7. It will rapidly find A equals 18, and then rapidly within there find B equals 7. So almost instant to get that one. What about where A is 10? Well, it'll instantly find where the A equals 10 group is located, and then it'll just read off all of those. So again, that will be extremely fast. Select star from table where B equals 7. Well, now this index won't help us here because the B equals 7s are sort of, well, it's missing here, it's included here, and it's missing here, but there's no way of rapidly going to an individual value of B because the way we've defined the composite index, A is the dominant column and B is the secondary column. So if you're going to frequently be using this sort of command, then you would consider creating an index on B as well as AB. Okay, that's all I want to say about indexes. They really are a sort of a matter of trying things out, seeing how things work, analyzing what kind of queries you're going to be using most frequently, and then choosing the indexes wisely, knowing that you pay a cost in disk space for every index you choose. If something is huge but never changing, like an encyclopedia or a dictionary or something, then index lots of things. If something's not that big but changes rapidly, then you don't want to index things there because the time spent on rewriting the index will dominate the time that you've saved by using the index. Okay, so that's this video.